In the previous video, we talked about this simple communication protocol and how it can be used to communicate data very simply. But what could possibly go wrong? The issue comes in basically every one of these transitions. What if we mistransmit? What if there's noise on the line and the start pulse isn't received correctly, or a long pulse is mistranslated as a start pulse and we're out of order? Or what if we have some noise and a long pulse is interpreted as a short pulse, or vice versa, and all kinds of things can go wrong here. And I'm also not even handling the case where we start listening in the middle of a message. What happens then? In this case, we'd be waiting for the start pulse, the next message. Is there a way we can transfer that data or save some of that data as we go across? There's lots of different things that could go wrong in this situation, and we want to make sure that we can handle those. A couple of ways that we can do that is with these error correction codes. The first one is parity, the simplest way to do that. And parity comes in even or odd parity flavors. We can also use checksum or cyclic redundancy check, CRC codes, to verify that a message was translated and transmitted correctly. Calculating parity is the easiest of these error checking procedures, and it's often included as the ninth bit per byte because it's so easy. It's only one bit typically, and basically the process is that we count the number of ones in the message, and if we are doing the even parity flavor, then we're going to if the number of set bits is odd, we set the parity bit to 1, which makes it even. If it's already even, we set the parity bit to 0 and it stays even. So the idea is we want to make the even parity, the entire message, including the parity bit, we want to make it even number of bits. Similarly, for odd parity, if our message is even, we want to set the parity bit to 1, which makes it odd, so that the entire message is odd, right? Now, the idea is we transmit the message and the parity bit, and the receiver calculates even or odd parity, whichever one both endpoints have agreed on. And if the parity bit is 1, or if the parity of the message is 1, either it's even or odd parity, then the message something has gone wrong, right? Because we're calculating the other format, and if that is the case, then something has gone wrong and there has been a bit flip and we should request a retransmit. Let's look at an example of even parity, right? So Alice wants to send 1001. Let's think about this for a second. Is there a binary operation that we can use to calculate parity? And think about it. We only care about whether a byte or a sequence of bits is even or odd, and we want to add them together. How do we build our adders back in 230 or 120? So the way that we can calculate even parity is by using the XOR operation. All we have to do is XOR the bits of the message together, and that gives us even parity. So in this case, I've got 1001. There are an even number of ones, and that gives me a 0 parity. So the entire message that I'm going to transmit is 10010. Alice sends this to the other side, and the problem occurs during transmission. There's some kind of flaw, and Betty receives 11010. Betty then calculates her parity and finds out that it ends up, for the entire message, all 5 bits, that it equals 1, and that indicates her that there was some kind of error. She doesn't know where the error occurred, but some kind of error, and she can request a retransmit of that particular message, and hopefully that everything works out over time. Now let's look what happens if we get a really bad transmission error. In this case, Betty receives 11000. 2 bits have been flipped. So we've got this bit here that has been flipped, and also the bit at the end. If Betty calculates the parity of this, everything looks good even though 2 bits have been flipped. So this particular form of error checking is only for very simple errors like single bit flips, if that happens in an entire message. So we need something a little more sophisticated to handle more complex error correcting or error catching coding. Checksum is the next level up, and the idea here is that we take a bunch of bytes of a message and we add them all together, and that gives us the checksum. We take that sum and take the 2's complement of the sum and add that to the message itself. So here's an example where the transmitter is going to send these 6 bytes all the way down this way. If we add them all together, ignoring overflow, we don't really care about that right now. If we add them all together, we end up with a checksum of 0, 4. We take the complement of 0, 4, flip all the bits and add 1, and we end up with a checksum value of FC. We transmit that along with our 6 bytes. The receiver goes through and adds them all together, including the checksum byte, and they should end up with 0, 0. That way we know that all of the bits in the 6 bits that come with it have been validated, including the checksum byte. So in this case, if 1 or 2 bits have been flipped, it has to be very precisely the right bits, because it can still be possible that we can't detect an error if the right bits are flipped. If we have both a bit flip in our checksum and a bit flip in our message, or several bit flips in our message, we can get a checksum of 0, but that's even less likely. So this one helps us identify whether an error has occurred during transmission. Even more complicated, but really easy to implement in hardware, is cyclic redundancy check. And the way we do this is we basically calculate a binary polynomial using XOR. So here we have a shift register. Our original message gets put into the shift register, and as we shift the bits through, we're calculating the total checksum for this thing, and the checksum that results are the bits below here. So my checksum using CRC was 1, 0, and we can transmit that along with the message. Similarly, if I transmit that along with the message, what I end up doing as it cycles through is we end up with all zeros, and that checks to see that the entire message has been received correctly. And this one is more advantageous because we're not sending an entire new byte, we're only sending the lower bits of the checksum, and we can save some extra room and still know that the extra data above the data we've sent along with it is totally valid. So we've got a few ways of detecting errors that occur during transmission, but not really correcting them. There's a bunch of different ways to do the correction. There's like Hamming codes and all kinds of other higher level error correction that we can include, but typically the correction just involves saying, hey, I got a bad byte, can you send it again, as part of the upper level protocol. And there's lots of different ways to handle these types of errors.